Welcome to the ninth lecture of Probability for Machine Learning series, in which today we are going to cover probability density function and cumulative density function, which is PDF and CDF. So let's go to our tablet screen to discuss more about the topic. But before starting the topic, first let's write the heading. Sorry, I have not selected the ink. Probability PDF. Short form is a lot better. PDF and CDF. Right, so these are the topics that we are going to discuss today. But before starting the topic, first I will like you to solve a question which I am also writing here. The question is, you are running to the bus stop. You don't know exactly when the bus arrives. You have a distribution of probabilities you show up at 2:15 p.m. What is the probability of wait less than 5 minutes? The distribution is in the next page, which is here, right? So let's read the question together. You are running to the bus stop. You don't know exactly when the bus arrives. You have a distribution of probabilities, which is mentioned here, right? You have a distribution of probabilities. You show up at 2:15. What is the probability? This is a very simple question, no rocket science or no mathematics. No, mathematics is required to solve this question. So you are arriving at 2:15. You are arriving at this point, and you have been asked what is the probability of wait less than 5 minutes. So you will wait till 2:15 till 2:20. You will not wait from 2:15 to 2:10. You will wait from 2:15 to 2:20. And this is a distribution of the probabilities that the bus will arrive. So of course, this will be our probability. The value of this here. This is our probability. So as you can see, currently these chunks, the graphs and the chunks are divided in the interval of 5 minutes. So from 2 to 2:05 to 2:10 to 2:15 to 2:20 to 2:25 to 2:30. But let me give you another scenario, which is this one. Let me just increase the size of the graph. It is getting a little bit blurred. Yeah, this is. Now the time is divided into 2.5 minutes chunks, right? So if this is 2, this will be, I have not selected the ink. Yeah. So if this is 2, this will be 2 minutes. What this will be? 2.5. What is the 2.5 minutes? 2:30. No? 02 p.m. Because the 30 seconds you cannot denote, or you can denote 2:30, and similarly this will be 2:05:00, and similarly. But now what is the difference of this graph from this graph? The time chunks in the newer graph is divided in the 2.5 minutes. So this bin denotes 2.5 minutes, and similarly this bins denote 2.5 minutes. In the question we have been asked what is the probability of wait less than 5 minutes. So we are going to take, let me just change the ink for the clarity. So we will take the summation of these two bins, right? You notice something. What if the bins have been reduced to infinitely small time intervals? then you will not be able to observe the bins. You will observe a clear smooth line that is running across the graph, right? And now you have been asked what is the probability of wait less than 5 minutes. So what you will do, you will find this is the 15-minute, this is the 20-minute. So what you will do in this case, you will find the area under this graph, right? Now this becomes, when we are talking in discrete terms, we use probability mass function. But when we are talking in continuous terms, in this example, the probability is continuous. There is no breaking between the probabilities. No sudden changes between there is sudden changes, but not like the probability is initially this and then it becomes this. There is no breaking between the probabilities, right? Then we refer to that random variables as continuous random variables, and in the concept of continuous random variables we use probability density function. So this is a probability density function, and to find the necessity probability that we want, for example, we want to find the probability of wait less than 5 minutes. So we will find the area under this graph. This will be our probability. So what will we do to find the area under the graph? We integrate. So the integration of PDF equals probability. Now let's write the definition of probability density function. The probability density function, the PDF of a continuous random variable of a continuous random variable represents the relative likelihood of various values. If you don't understand the definition of the PDF, this is very technical definition, but if you don't understand the definition of PDF, there is no problem. The concept of PDF is very simple, as you can see in this graph. So this is the PDF of the distribution. Now let's discuss some properties of PDF. Properties of PDF. These are very simple properties. The first property is, let me write first and then I will explain. This will be small f of x. Right. The first property is very simple, that the integral of PDF cannot exceed 1. Why? What is the integral of PDF that we have discussed just right now? The integral of PDF is the probability. Since the probability of any outcome cannot exceed 1, the integral of PDF will also not extend 1. Now the second, and this is also a very basic property, integral minus infinity f of x is always less than equal to 1. So this is also a very simple property. This means that let me just take the help of the graph, or the minus infinity corresponds to here. You can write instead of minus infinity 0 because there is no probability of negative outcomes. Okay, but we write minus infinity, right? So what is the integral of PDF? Again, probability. This is the probability. No, wait. This is always equal to 1. I have mistakenly written the property wrong. So what is this? This means that the probability of whole outcome is always equal to 1, right? So this is very basic rudimentary properties. Now, let's see some different types of graphs of PDF. PDF graphs. Very simple graphs of PDF. So let's draw our firstly y-axis, then x-axis. So the y-axis corresponds to probability, and the x-axis corresponds to, you can say, for example, time, right? First I will draw the graphs and then I will explain. Or let's explain simultaneously, right? So what this graph says, this is not a breaking graph. Let me draw it once again. Yeah, this graph is also okay. So what this graph symbolizes, this says that for initial times, for the starting times, the probability of any function is high, and as the time increases, the probability reduces. So this graph symbolizes these types of events. Let's draw another graph. So again, our y-axis will correspond to probability, and our x-axis will correspond to time. Let me just draw once again. Okay. Hmm. So what this type of PDF graph symbolizes? This symbolizes that irrespective of the time, which is here, for example, let me write it A, let me write this as B, right? So this graph symbolizes that irrespective of the time between A and B, the probability is constant. But if the time is lesser than A or greater than B, then probability is zero. So this can be a symbol. No, this not can be. This is the graph of, you can say, uniform random variable. This is the graph of uniform random variable, right? On this note, let's discuss some properties of uniform random variable. Uniform random variable. The above graph is of uniform random variable as we have discussed right now. So what is the PDF of uniform random variable? PDF. Its PDF is simply b minus a. Sorry. It is 1 upon b minus a. The b is here, a is here, and simply the PDF is 1 upon b minus a. Now what is the expectation? Expectation is average. Is simply b minus a by 2. And the variance is simply b minus a whole square by 12. Now let's do a sample question of uniform random variable that also includes PDF that we have discussed just now. And the question is very much similar to the question that we have discussed in the starting of this lecture. So the question is, you are running to a bus stop, are running to a bus stop. You don't know. The same question is exactly similar, just with one tweak. You don't know exactly when the bus arrives. When the bus arrives. Uh, arrives. You believe all time between 2 and 2:30 are equally likely. This term is very important to be focused on. Equally likely. You show up. You show up at 2:15. At 2:15. What is the probability of wait less than 5 minutes? What is the probability of wait less than 5 minutes? Less than 5 minutes. This is a very simple question. I suggest you to stop this lecture and at least try to attempt this question, because this is very simple question, right? So I hope you have paused the lecture and at least try to attempt the question. Now let's read the question together. You are running to the bus stop. You don't know exactly when the bus arrives. Very simple. You believe all times between 2 and 2:30 are equally likely. In this case, all the bins that we have drawn, for example, the bins that we have drawn here, all the bins have equal sizes because we expect all the times are equally likely between 2 and 2:30, right? So our graph will be simply like this. This will be our A, which is 2 o'clock. And this will be our B, which is 2:30. Let me just, yeah, which is 2:30. Now, we have shown up at 2:15. We have shown up at 2:15. And we have to find the probability of wait less than 5 minutes. So we will wait till 2:20. Very logical. So we have to find the area under graph of this shaded red part. Let me shade it. This shaded red part. So we have to find the area of this shaded red part. So this is very simple. Right? So what is the PDF that we have discussed here? PDF is simple. 1 upon B minus A. Right? What is B here? 30. Let's assume B is 30, then A is 0. So the PDF is PDF is 1 upon 30 minus 0, which is 1 upon 30. So we can say that this y-axis, let me write it here, probability, and here time. So we can say this thing will be 1 upon 30. Very simple. Now we have to find the area under this graph, right? So every small bin is 1 upon 30 of 1 minutes. Simple. So PDF for 5 minutes will be 1 upon, not PDF, probability, 1 upon 30 multiplied by 5, which is 1 upon 6. I think so. Yeah, I am correct. And what is 1 divided by 6? 0.0164 0 6 36 4. It is simply 0.16 bar, right? The another way to solve this question, this is a very, you can say, rudimentary way or jugadu way to solve this question, right? Now the other way to solve this question, that is the technical, you can say the technical solution is we have to integrate the PDF, right? We haven't integrated the PDF yet. We have just used a very easier way, right? Not a technical way. So let's write the PDF here. PDF of the uniform normal variable, which is 1 upon B minus A, which is 1 upon 30 minus 0, right? 30 minus 0, right? Now we have to integrate this PDF, right? So we have to integrate. We will not put the values of B and A now. 1 upon B minus A dx integrated from 0, not 0, 15 to 20, right? Yeah. So if we integrate this PDF, this becomes the probability of this becomes the probability, because integration of PDF is probability, is equal to x upon B minus A, simple box 15 to 20, not box, brackets, right? Now let's put the value of B and A. The value of B is, as discussed, is 30 and the value of A is 0. And the limits are here from 15 to 20. Now let's first put 20 here instead of x. 20 upon 30 minus 15 upon 30. So this is 5 upon 30 or 1 upon 6, which is equal to 0.166 bar. So this is the more appropriate way to solve this question. Or you can say this is the more technical answer. Technical, not technical answer, technical solution to solve this question. Now, let's discuss exponential random variable. Exponential random variable. This is a very easy concept. Let's see its definition. An exponential random variable, exponential random random variable x is the amount of time amount of time until success. Until success. This is also a very easy, you can say easy type of a continuous random variable. But if you are not able to understand it by the definition, there is no problem. When you will do a sample question on this topic, which we are going to do in this lecture only just now, it will be understood like a charm, right? So now let's discuss the PDF of this exponential random variable. PDF is lambda e raised to the power minus lambda x. Yeah. Now the expectation is very simple. That is 1 upon lambda, and the variance is also very simple. That is 1 upon lambda square. These are very easy topics, right? Now let's do a sample question on this exponential random variable, right? Based on a based on a historical data, major earthquakes, major earthquakes, earthquakes. By the way, I just wanted to tell you, I forgot to tell you this. This lambda is the average rate. The average rate. And the value of E is 2.71. It is very, you can say, rudimentary concept. I am talking about the E. The lambda is average rate. It is a similar concept that we have discussed in the Poisson theorem, right? Now let's discuss let's solve a question, right? So firstly, I'm writing the question, right? Magnitude 8 plus happens at a rate of at a rate of 0.002 per year. What is the probability of of major earthquake earthquake in the next 30 years? In the next 30 years. This is very simple question. Pause the lecture and at least try to attempt this question. I hope you have paused the lecture or at least have read the question by yourself. Now let's read the question together. Based on a historical data, major earthquake with magnitude 8 plus happens at a rate of 0.002 per year. What is the probability of major earthquake in the next 30 years? Very simple question. So as you can guess till now, this is the question of exponential random variable. So let's write its PDF first. Answer. PDF of the exponential random variable, as we have discussed just now, is lambda e raised to the power minus lambda x, right? So here lambda is 0.002, right? 0.002. Here lambda is 0.002. But as we have discussed, the PDF is not the probability. The PDF is the differentiation of the probability. To get the probability, we have to integrate the PDF, right? We have to integrate the PDF from 0 to 30 years, lambda e raised to the power minus lambda x. So let's put the value of lambda. Or not put the lambda. First, let's solve the question and at the end we will put the value of lambda. So since lambda is a constant value, we can put the lambda outside the integral 0 to 30 e raised to the power minus lambda x. In the integration, there is a property called as, not called as, written as e raised to the power cx. Integration is simple, 1 upon c e raised to the power cx. A very, you can say, basic property of integration. Now let's simulate it here. So lambda, since c has gone into the denominator, integral 0 to 30, 1 upon lambda, not integral, sorry, 0 to 30, 1 upon lambda, e raised to the power lambda x, which will be with the minus sign because the lambda is with the minus sign. And since again the lambda here is constant, we can move the constant out of the brackets. Lambda upon lambda with a negative sign, which is very important. E raised to the power lambda x 0 to 30. This lambda and this lambda will get cancelled out. Now we have to find e raised to the power 30. E raised to the power 30, not 30, sorry, 0.002 multiplied by 30 minus e raised to the power 0.002 multiplied by 0, which will be 1. So this will be 1 because anything raised to the power 0 is 1. And this will constitute with a minus sign. Now let me just calculate the value of this part because I don't know the value of this part, which I should know, but I don't know. Calculator. This will be, yeah, e raised to the power 0.002 multiplied by 30, right? This is simply, why this is coming? Oh, I have removed the negative sign from here. That was I was a little bit confused here. Simply minus sign will be here also, right? So this will be equal to minus 0.94 minus 1, which will be minus 0.06. 0.06. And as we know, minus minus equals 1. So this will be 0.06. So the probability of the earthquake in the next 30 years will be 0.06. Very simple and easy concept. Now let's move to the next part of this lecture, which is the discussion of CDF, which is cumulative density function. So first let's write the definition of CDF. So what is the definition of CDF? CDF is a closed form, or just let's remove it. CDF, I am going to write a very easy definition. The CDF is integration of PDF. Very simple definition. What is CDF? It is simply the integration of the PDF. It is denoted by capital F of x, and the PDF is always denoted by small f of x, right? Just I wanted to make this concept, write this concept. Yeah. So now let's derive the CDF of exponential random variable. So as we have discussed just now, CDF is simply the integration of PDF. Okay. So we know the PDF of exponential random variable, which is lambda e raised to the power minus lambda x. And what we have to do? We have to integrate it simply from 0 to x. Very simple. Let me just write 0 a little bit neatly, 0 to x. Since lambda is a constant value, we can put lambda outside the integral, right? So lambda integral 0 to x e raised to the power minus lambda x. And as we have discussed just now, a basic integral property, which is integration of e raised to the power cx equals 1 upon c multiplied by e raised to the power cx. So we are going to apply this property here. Lambda brackets, because the integral has gone, minus 1 upon lambda e raised to the power minus lambda x. We can simply put this lambda outside the brackets. So this will be minus 1 e raised to the power minus lambda x from 0 to x. Now let's put the limit in the equation. So minus 1 multiplied by, well, let's put the square brackets instead of curly brackets, e raised to the power minus lambda x minus 1. And since there is a minus sign here, minus minus plus. So we can write 1 minus e raised to the power minus lambda x. So this will be the CDF of exponential random variable. Exponential random variable. So in the above question, in which we have used integration to derive, so instead of using PDF, we could have used CDF, right? Now let's see some graphs of PDF versus CDF, right? The same graph of PDF and the same graph of CDF. So this will be the y-axis will be our probability, and the x-axis will be our time. If the graph of PDF, so this is the graph of PDF, graph of PDF. So this is the graph of PDF, mind you. So if the graph of PDF is like this, right? It is not touching the x-axis, right? So if the graph of the PDF is this, then the same graph for the CDF will be this. Let me draw it. Okay, same graph of CDF will be this. Will be 1. This graph is also never touching this dotted line, right? So this marks the end of the lecture. I hope to see you in the next lecture soon. Till then, stay safe.